Okay, thought we'd do a few more problems, and it was a good time to split that other video anyway, since I thought there was something that was going to blow up on me. All right, anyway, we're going to do problem number 56 on page 281. So it's the same thing as the last time. Find the absolute max and absolute min for this function. F of t equals the cube root of t times 8 minus t. And we're only going to be looking at 8 minus t on the interval from 0 to 8. While we're at it, we might think about what this function has as its domain. Cube root of t has no problems anywhere. 8 minus t has no problems. The product is certainly not going to have any problems. So this function is defined everywhere. Okay, so looks like I've got to think about this a minute before I take the derivative. I'm kind of tempted to not use the product rule. I'm tempted to multiply this out because another way to think of this is as t to the 1/3 power times 8 minus t. And if I multiply that out, it'll be 8t to the 1/3 minus, now t to the 1/3 times t to the 1 will be t to the 4/3. And it's a little easier to calculate the derivative of this thing. So the derivative is going to be 1/3 times 8, so that's 8/3 t to the 1/3 minus 1, which is minus 2/3. Minus, bring down the 4/3, and you get minus 4/3. T to the 4/3 minus 3/3 is 1/3. Okay, so that's the derivative. Now you'll notice that once again here with this t to the minus 2/3, that's 1 over t to the 2/3. And that expression does not exist when t equals 0. So here is a place where we pick up another critical number, but actually we already had it. Remember, if we're going to be detectives, we've got to think about 0 and 8 as being possible suspects for where our maximum and minimum might be. And 0 already is an endpoint, so the fact that it makes the derivative blow up here doesn't matter, doesn't add anything. I'm already considering 0 as a suspect. Okay, so where else are we going to have critical numbers? Well, the only other places where we get this derivative equal to 0. So we set it equal to 0 and try to solve for t. So once again, I think I'm going to multiply both sides by 3 to get rid of those fractions on the bottom. And then let's see if there's something I can do to, oh yeah, look at this. What if I multiply both sides by t squared? T to the 2/3. Just multiply both sides of this equation by t to the 2/3. Of course, nothing happens on the right. You're getting 0. But on the left, you have to distribute t to the 2/3. T to the 2/3 times t to the minus 2/3 gives you 1. So you're just going to be left with 8. Now, t to the 2/3 distributes here, and we multiply it, and we're going to get 4 times, what's t to the 1/3 times t to the 2/3? That's t to the 3/3, or just t. So 8 minus 4t equals 0. Good grief, t equals 2. So now I have 3 suspects, and only 3 suspects, 0, 8, and 2. So we go back and plug them all in. F of 0 is what? Well, that would be the cube root of 0, which is 0, times anything. Well, that's going to be 0. Okay, let's try 8. What's that going to give us? F of 8, we plug it in, and the cube root of 8 is 3. Oh, wait, we're multiplying by 8 minus 8. 3 times 0, so that's 0. Now that's boring. Okay, and then we have one more critical point, and that's where t equals 2, so we have to calculate that. What's that going to give us? That's going to give us the cube root of 2 times 8 minus 2, which is 6. So 6 times the cube root of 2. Well, okay, I can tell what's going to happen then. We have Only 3 critical points. 2 of them are endpoints, and 1 of them is in the interior, somewhere between 0 and 8. So here's the situation. F of 0 is 0. F of 8 is 0. And f of the cube root of 2, which is somewhere around here, f of the cube root of 2 is going to be, f of 2, I'm sorry, it's getting late. F of 2 is the cube root of 2 times 6. Well, I don't know what it is, but it's positive. It's up there. Okay, so I ask myself, this is a continuous function, right? And it's going from here to here to here, and there are no other critical points. How can that be? Could it do something like this? Well, no, because there'd be a critical point, right? So that can't happen. So there's no way to get from here up above this point. So this point must be our absolute max. Similarly, is there a way to get down below the x-axis? No, because if you get down below, you have to start from here. You could go up and then down, but look, you get critical points. Anytime you turn around, you're going to get a critical point. Can't happen, right? So the function is going to basically have to go something like that. It can wiggle, but it can't turn around. That's no good, right? So it has to keep going down from this point. So that's it. We have one absolute max, and we have 2 absolute mins which are equal, both of them at 0. That's as low as this function gets on the interval from 0 to 8. Okay? So that takes care of number 56. Let's try number 61. All right, for number 61, same context, but this time we have a log function to play with. And this is f of x equals the log of x squared plus x plus 1. And this is on the interval from -1 to 1. All right, so you might be interested to know what's the domain of this function. And that means that we have to think about what we're plugging into the log. We're not allowed to plug in 0. We're not allowed to plug in anything negative. So what about this x squared plus x plus 1? That's a quadratic polynomial. And I wonder, is this thing ever equal to 0? I don't think this factors. If you pull out the quadratic formula and say, when is this equal to 0? You get x equals minus b, b is 1, plus or minus the square root of b squared, which is 1, minus 4 times 1 times 1, all over 2 times 1. And oops, this is 1 minus -4, -3. So no, there are no real solutions. Can't happen. It can't be equal to 0. And yet this is a parabola, and it's obviously going to be positive. I'm not going to be able to make it 0, so I can't make it negative. So this parabola always stays above the x-axis. So what that means is that this number is never 0, never negative, and so the log is going to be defined for all values of x, in particular for all of these. Okay, so where are my suspects? Well, there's -1, there's 1, and we need to calculate the derivative to see where the derivative is undefined or where the derivative is equal to 0. So I calculate the derivative of log, and I get 1 over x squared plus x plus 1. That's the derivative of log of something, except that the chain rule comes along and says, wait a minute, multiply by the derivative of what's inside there. So we end up with this factor of 2x plus 1. So this is 2x plus 1 divided by x squared plus x plus 1. And now we ask, is it possible for the derivative to not exist? Well, the derivative wouldn't exist if the denominator turned into 0. But we've already analyzed that x squared plus x plus 1 cannot be 0. Quadratic formula told us that can't happen. So this function has no critical points of the second type, no places where the derivative does not exist. So the only critical points that we can get are places where 2x plus 1 equals 0. This is a fraction. The only way it can equal 0 is to have the numerator equal to 0. So that means 2x equals 1, no, sorry, equals negative 1, x equals minus a half. And minus a half is perfectly fine. It's in that interval. So now I have another suspect. This guy, and this guy, and this guy are all suspects. They are possible absolute maxes or absolute mins. So I plug them all in. What is f of negative 1? Well, it's the log of negative 1 squared, that's 1, plus negative 1 is 0, plus 1. Log of 1, I can do that. That's 0. Okay, what's f of 1? F of 1 is natural log of 1 plus 1 plus 1. Natural log of 3. I don't know what that is, but it's bigger than 0. I'm sure of that. And what's f of negative a half? Well, it's going to take some work. This is natural log of negative a half squared is 1/4 minus a half plus 1. And that's going to be natural log, oops, run out of room. Natural log of a half minus, I'm sorry, a fourth minus a half. Well, let's go the other way. 1 minus a half is a half, plus a fourth is 3/4. So this is the log of 3/4. And I don't suppose you know what the log of 3/4 is. I don't either, but I can tell you that it's going to be a negative number because 3/4 is less than 1. And remember what the log function looks like? It's just like that. And this point is 0. So the log of 3/4 would be like that. So what do I know from all this? F of negative a half is the log of 3/4, which is a negative number. It's negative. F of 1 is the log of 3. This is going to be a positive number. And f of negative 1 is 0. So these are my only critical points. Negative 1, 1, and negative a half. Nothing else strange is happening on this interval. This function can't blow up, doesn't have any negative, doesn't have any problems with this because that interior thing, x squared plus x plus 1, cannot be 0 and it can't be negative. So there's nothing strange happening. So these are the only 3 critical points. And this is a positive value. The other guys are 0 or negative. So this 1, x equal to 1, has to be the absolute max. And then this guy, where we get a negative answer, negative a half, that's going to be our absolute min. All right. Now, again, this is an example where it may be hard to believe, and who knows what this thing looks like. So let's take a little trip over to Maple, since I still have that open, and get Maple to calculate this thing for me. Log of x squared plus x plus 1. So here is the log of, oh, I need to type it in. Natural log of x squared plus x plus 1. Oh, that didn't work. I missed the squared. X squared plus x plus 1. Okay, better. Now let's plot that guy. And I need this on the interval from -8 to 8. And I think that's what it was. I lost the problem. I should flip back and look. On the interval from, oh, -1 to 1. Okay. So on the interval from -1 to 1, so I suppose we should zoom in on it, but you know, you can see from here what's going on. There is an absolute min right here. And then let's just go ahead and do it. So I want the interval for x equal to -1 to 1. And we'll change the y while we're at it. So the negative 1, that should be, let's just make it reasonable, negative 1, and make it go up to 3. Okay, so what's going on here? Well, on the interval from -1 to 1, that is where we were, isn't it? -1 to 1. So we have a function that goes like that. So it looks to me like -1, no, like this guy, whatever that is our absolute min, and we're going to have an absolute max at 1. What did we say? We have an absolute max at 1, and we have an absolute min at -0.5. -0.5. Looks pretty good. Absolute max at 1. Okay? So, what we see is that this approach gives us answers. It takes a lot of doing, and you may be wondering, well, why don't I just, what's the point? Why don't we just put it into Maple and make it graph it, and we can look at the thing? Well, there's a lab coming up that will answer that question to a large extent, but the short answer is that you cannot tell from looking at the graph what's really going on. There are plenty of examples where the graph is very, very misleading. So you need to do the analysis to really understand what's going on. This stuff is all the analysis. Okay? So that's about it for now.